So welcome back. Okay, so one more thing I wish to emphasize. So next week, okay, there's no lecture. Okay, no lecture for next week. Okay, no lectures for next week. So okay, today we are going to still go to the second lectures for the satellite positioning. So as you mentioned, so quickly go through the teaching plan. Okay, satellite positioning. So week 4, there's no lectures. Okay, so week 5, okay, one more week for the satellite positioning, and week 6, okay, tutorials for the GPS positioning, and okay, week 7 we are going to start with the visual-based positioning, and also we have one midterm test. Okay, it's like several questions, and you get 3 hours to answer the questions. And after midterm, okay, we are going to start with the sensor fusion. So for example, we have the GPS and have the like inertial measurement units. So how to integrate the different information sources from different sensors. So after that, we are going to have okay. So luckily, I mean, by this week we have 11 students. So I thinking, yeah, but we are luck. We have like 11 students. No one jobless lecture so far. So it means I think we can have at least 1.5 lecture to for the presentations. Okay, so I mean in this lecture I may suggest like each of you, okay, can make a presentation. So instead of like group presentation, because we have very limited number of students. So because previously we have like 40 or 50 students, so that's why we make the presentation into groups. Okay, so this is going to make up around like 20% of the final assessment. Okay, so after that we are going to have the final exam. Okay, with open book. So as we mentioned last week, have you looked into the slide? Have you looked into the slide before? So I mean, in today's lecture, we are going to talk about GPS, and also we have some example codes, okay, based on the Python. So in last week, by the end of last week, we talk a little bit about, like you can spare some time to look into the slide first. So any of you have looked into the slide before? No? Okay, so I can slow my pace for today. Okay, so today it's going to be start with the first part of the satellite positioning. So the basis and single point positioning. So we have 3 different levels of the satellite positioning. So for example, if we mentioned in the very first lecture, so if we directly use the range measurements from satellite. Okay, so this is called a single point positioning. So without any assistance from reference station. So solely based on the measurement from satellite. Okay, this is called a single point positioning. Okay, only based on the range. So this is the first level of the positioning. Okay, the accuracy is around like 3 to 5 meters. So I mean, by today we are going to talk about the GPS positioning with accuracy of 3 to 5 meters. So the second level is it's called differential GPS. It means we have some correction data from the reference station. So for example, in Hong Kong, all the correction data are fully available to us. So this can lead to accuracy of like sub-meters, maybe like 0.5 meters of accuracy in open sky. So all those accuracy are based on the assumption that you are in an open sky. So the level 3, okay, the real-time kinematic, okay, we always say this is RTK, so you can achieve like the 5 centimeters accuracy, okay, like this. So this is also based on the collection data from the reference station, and also it's make use of another measurement. It's called carrier phase. Okay, later we are going to introduce this. So let's start for today's lecture. Okay, the background is like, okay, outline includes the background of GPS. So actually we have mentioned a little bit for the background of GPS in the last week. So the second part is about GPS overview. Okay, like some like the basic flow charts of the GPS. So the last one is the principles of the GNSS. We are going to talk about like for example, like how to do the single point positioning. So in here we have GPS and the GNSS. So we are going to start with GPS, and the GNSS is this is the combination of the multiple satellite system, like for example, like GPS and BDS from China and the GLONASS from Russia and Galileo from European Union. So this is roughly about the outline. Okay, so as we mentioned, so the GNSS, this is the combination of the multiple satellite system. Okay, of the, for example, like the GPS, okay, global positioning system, this from US. So the second one is the GLONASS, this from Russia, okay. So usually like for GPS, we have around like 30 satellites. So for this one, we also have around like 30 to 34 satellites for Russia. So this is a satellite system, okay. GPS is a satellite system. So this is one more, another satellite system from Russia, and this is from China. Okay, so this, I mean, for BDS, we call it Beidou satellite system. So currently we get into the third generation of the BDS satellite. So currently we have around like 34 satellites from Beidou satellite system, and this Galileo is from European Union. Okay, so it's roughly like we have 4 major satellite system. Also, we have several satellite system, like for example, like this is called regional system. So for the first row, it's global satellite system. It means as long as you have a smartphone or you have a receiver, so you should able to receive signals from anywhere in this world. Okay, that's why this is called global system. So the second row, this is regional system. For example, this is specifically designed for the for the Japan. Okay, because Japan is, nationally is quite small area. So the last one is from India. Okay, and I insist this is specifically designed for India. Okay, so for example, they can do some augmentation. So for example, they can combine the satellite from GPS or maybe BDS plus their own regional system to improve the accuracy of their global positioning. So there are 3 important service of GNSS. So of course, the first one is like the active positioning. So for example, like we go anywhere with a smartphone, so you can use the GPS as long as you have the satellite visibilities. Okay, you should able to receive signals from the satellite. So this is so called the active positioning. Okay, so another service. Okay, let's intersatellite link, for example, like the LEO satellite. So those 2 parts are not usually used. Also, you can use the message for the communications. For example, currently we have the low orbital satellite. For example, the Starlink. Okay, Starlink company is from Elon Musk. So they have their own LEO satellite. So LEO satellite means LEO, the low orbit satellite. So this can use for like to do the phone calls. Okay, the communication is based on those low orbit satellites. So this is another service for. But in this course, okay, we are mainly talk about the actual positioning. Okay, for the different application purpose. So for in terms of the data source, okay, just data source, we have several. Like so this is more like a reference station. So for example, we have the check-in stations from global to regional. I put this figure. I want to say, so in Hong Kong we have several like the check-in stations. For example, just now I mentioned like we if you want to achieve the real-time kinematic positionings, so need to have the correction data from stations, right? So those are the stations. So in Hong Kong, so it means you can receive the correction data from those stations to provide the high accuracy positioning. So we are going to mention this in a later slide. So for example, like in different countries in this world, okay, the red dots means the stations. So what the stations includes? So usually in those stations, they have a very accurate, high accuracy, geodetic level GPS receivers. They receive a message from the satellites almost all the time. So with very high accuracy and open sky. So in this area, there's almost no signal reflections. There's no signal reflections in this area. So those reference stations can receive a message from the satellite and also helps to monitor the healthy conditions of the satellite. For example, like for those reference stations, their position is already a known variables. Okay, pre-geodetic level, okay, they already get the locations accurately. So, and also for the satellite's trajectory, it's already a known variable. So it means at each of the time, so the range measurements from satellite to receiver should be a known variable. So if there are some abnormalities from the satellite, so those stations can observe, okay, those conditions. So for example, in Hong Kong, okay, so this is Hong Kong, we get 19 GN stations. Okay, for example, when we I think in Hong Kong, like in PolyU, so in PolyU we have quite a few professors working on the satellite positionings. So they usually use the measurement, the station correction from HKSC. So this is PolyU. So this is a station. So the station is usually like located in the roof of the mountains with very good satellite visibilities. So those are the stations. So in terms of, because GPS is a radio signal, okay? So you don't need to really remember those frequencies, just have a quick overview. So for different satellite systems, they have different frequency sources. So for example, for GPS, they have three. You can understand like the level L1 is a level 1, level 2, and level 3. So this is the three different generations of satellites. So for example, in 1970s, they launched their first generation of satellite. So like maybe 1990s, okay, look into the design of the last generation of satellite. They think, okay, we can do some improvements. So for example, the frequency, like the accuracy. So in this case, they launch the next generation of the satellite. Okay, we go to the Air 2. So for the BDS, okay, we also have different generations. So this is the frequency. So it means at least the frequency you can understand this. This is one of the name to discriminate for different satellite systems. They have different frequencies. So for example, like for BDS, we have different generations. So currently the latest generation is BD3. And also this is from Japan, this is from India. Okay, they have different frequencies. So this is the coverage in this I would say this greater Bay Area. So for example, the color here represents, so for example, the color here represents the number of satellites you can receive in this area. So for example, I think this is Greater Bay Area. It means usually if you take smartphones, okay, in this area, okay, I mean in the open sky, okay, if you get into the indoor, there's no signal. So if you get into this area, at least you can receive around like 30 satellites. Okay, this is already very much good enough for you to do the positioning, because as we mentioned previously, usually you need around like 4 satellites, okay, to the positioning. So in this case, like at least like in Hong Kong, okay, Hong Kong of course belongs to the greater GBA, so you can receive like more than 30 satellites in the open sky. I mean, this is based on the assumptions that can receive signals from different satellite systems, including GPS, BDS, and also the Granules, Galileo. So, okay, so that's why you can share this, you can enjoy a service from the satellite positioning in Hong Kong, because you can receive different satellite systems. So, as we know, the application for GPS is widespread. Includes like the GPS for example, like the GPS for smartphones, okay, and also includes. So for example, like GPS for smartphones. So in here is the resource, I mean, the applications for GPS for the cars. So the Waymo, okay, so the Waymo is previously is originated from Google. So I mean, on top of the Google, there's a mother company is called Alphabet. So know this one? There's a mother company on top of Google. It's called Alphabet. So Alphabet have several companies, Google and this Waymo. I mean, the Waymo is like kind of the same level with Google. So Waymo currently is I mean, one of the biggest company in terms of the autonomous driving research. So see, the positioning solution includes the GNSS RTK. So as we mentioned, the RTK is a level 3 positioning from satellite, from GPS. So it can provide centimeter levels of accuracy. So also it includes the INS. This is the IMU inertial navigation system, and also this is the LiDAR. This is the map. Okay, HD means the high precision map. So as we mentioned, you already get like centimeter accuracy from RTK. So why we still need to have the LiDAR, have the HD map? Any ideas? I mean, for RTK, we can already provide like centimeter levels. That should be good enough. I mean, like 5 centimeters should be already good enough for the driving. So why we still need to have the LiDAR and also the HD map? Because as we mentioned in the last week, the LiDAR is quite expensive, right? Because the GPS is not reliable. In like if I mean the surrounding with buildings, it can, I mean the satellite signals can be reflected occasionally. Okay, this is going to lead big position errors. So that's why we need to have a combination of the different sensors. So for second one is Ford. Okay, Ford is a big company in the field of the car manufacturing. So I mean, what I want to say is all those companies relies on the GPS, relies on the GPS. So the last level, okay, this is the level of automation. Because for the autonomous driving, okay, we have the definitions of the levels of automation. So if a level is around like 2.5, okay, it's like you can enjoy some autonomous functions like line keeping. Okay, so those some collision avoidance functionalities. So for the level 5, this means the fully autonomous driving. Okay, level 0 means fully drive by yourself. So this is a definition of the level of automation. So if you're looking into those solutions, I mean the GPS is almost always there. Okay, the GPS is almost always there. So in here is I mean, this is the testing in Hong Kong. So if you look into the performance, I mean, the error can easily reach around I mean, for the just a single positioning, error can reach around like more than 50 meters. So this is the big errors. I mean, for the cars, it's not acceptable, at least for the autonomous cars. So and also if you look into the RTK, so the error is around 10 meters. And also if you look into the availability of the results, I mean, only 2% of the times the RTK solution is available. So in this case, I mean, like 98% of the times the RTK is not available. It means cannot provide the positioning solution. So this is a big challenge in urban chaos. So that's why in in PolyU, we have quite a few professors working on this topic because Hong Kong, we have the data. Because in Hong Kong, you see that one of the key features of Hong Kong is like tall buildings, right? Narrow streets, tall buildings, and also, I mean, the good news is like in urban chaos, we have a lot of strong needs for accuracy positioning, right? For example, pedestrian navigation and the location of the cars. So this is roughly the overview of those positioning accuracy. So also we do one more test. Okay, so this is in the car park of PolyU. So we do this testing. Okay, do this testing. So for example, we like put several smartphones in these cars, and based on different models. For example, like the Oppo, Honor, and the Redmi Note. So this from several famous companies. You can find okay, the majority of the times, I mean, the majority of times, I mean, the course is kind of like mid-level. So if you look into the results, okay, we do testing in such kind of scenarios. Okay, so in this plot, okay, how to understand? So this is the longitude. Okay, this is the latitude. Okay, so the color here represents the errors. Okay, so the more yellow, okay, you get smaller errors. So more bluish means you get the stronger errors. Okay, yellow is smaller errors. If fully yellow, it means 0. So it means the yellow area usually corresponding to like kind of open sky. Okay, open sky or with good satellite visibilities. And Okay, so for this one, this is from three different from different smartphones. So if you look into this result, okay, so at least we can find for the three different phones, the Redmi and the Oppo, the performance is kind of similar. Okay, it's around 32 meters. Okay, 13 or like 12 meters. This is still a little bit large. I mean, in terms of precision accuracy, like 10 meters, it's already it's like from this wall to the corridors. Okay, like 12 meters. So this is already a big error. That's why we still have rooms to do improvements. So this is the objective of research, right? If I mean from the commercial side, if they have no problem, it means we don't need to learn this lecture. We don't need to know how to improve the accuracy of the smartphones. So it means, so guys, we still have a lot of rooms to improve the accuracy from GPS. Okay. So this is, I mean, for the first one, I mean the model, the first one is like the car. Okay, the smartphones is put to the cars. This is in the driving mode. So this one is like pedestrian holding smartphones. This is more like the directing. Okay, so I mean pedestrian navigation. So smartphone have the IMU. Okay, it can do the directing, and also they have GPS. Okay, they can do the satellite positioning. So at least if you look into results for pedestrian navigation, it's quite, the accuracy is much okay, terrible. Okay, compared with the car-based the driving mode, so the error can reach about 20 meters for the Honor and like 20 meters for the Oppo. So this is the results for the driving mode. Okay, pedestrian navigation mode based on three different phones. So for example, still for this open sky, okay, the yellow part means this area is smaller. So I mean from this we can find even we cannot identify the shape of the trajectories, right? Based on this pedestrian mode. So questions. So while the smartphone based position accuracy is much larger, okay, compared with the driving mode. Zenjun, any ideas? Just mention the first thing appear in your mind. Sorry, for example, like no worries, just mean okay. For example, like cars, the for example, like driving cars, you at least you have some constraints, right? So for example, if I drive a cars, okay, the vertical speed it should be 0, right? Because I cannot jump for a cars, and also if I drive a cars, okay, so let's say the lane line, okay, so of course I cannot, for example, like my horizontal, lateral speed for a cars should be 0, right? So those are very strong constraints that can be applied for the positioning estimation. So for example, like the vertical direction, the velocity is 0, and the lateral velocity should be 0. And usually the cars at a short period it should be constant velocity. So based on this model, we can easily like improve the accuracy. That's why, for example, go straight line, at least it can reflect it's a line. But for the pedestrian, I can just go anywhere. You see, I do not follow a specific model. Yeah, I can just walking around. For example, I can even get into indoors, right? So for example, for the cars, I can never get into the indoor scenarios, right? Because I cannot jump into the rooms. So in this case, at least for the car-based positioning, I can try to map my trajectory to align with the road structures. For example, this is the lane lines. At least should know that my trajectory should be parallel with the lane lines. So these are the strong constraints that can apply to improve the accuracy of the car-based positioning. So this is the reason behind. So that's why, I mean, for the vehicle mounted modes and the pedestrian navigation modes, I mean, the accuracy should be kind of different. So okay, so the reason is we have the I mean the essence is the signal reflection, but to be detailed, we have two different kind of problems. So for example, okay, so if the satellite is in this direction, okay, I can possibly receive the signals only based on reflections, right? because the direct transmission is, blocked by these buildings. It means in such kind of scenarios, you only receive the reflected signals. For example, if there's no, if no buildings on this side, you cannot receive the signals because no buildings to reflect the signal. So again, so this is called non-line of sight. So it means, okay, non-line of sight. So the signal is only received by the reflected transmission routes, right? Okay, so this is non-line of sight. So for this one, okay, if the satellite is in this direction, actually this can be directly received because there's no blockage in the direct transmission routes. But the signal can also be reflected from the same satellite, reflected, and then you receive it. This means this is called multipass. Multipass is this is the combination of the direct signal transmission and the reflected signal transmission. This is the combination of the both. So this is non-line of sight, which means the direct signal transmission route is blocked. But potentially you can receive the signal still because the signal can be reflected by the building on the one side and then be reflected and received finally, okay? So this is the NROS and the multipass. So for example, okay, this is a snapshot in Hong Kong. So how to understand this figure, okay? So this white area corresponding to this sky area, okay? This is quite limited, right? Okay. So those circles with numbers represents the satellite index. For example, 98 GPS satellite. Okay, this is the index. So we can find the majority of satellite is like from this two sides. It's located in the gray area. Gray area means the building area, which means, so the red satellite means those satellites are actually blocked by the buildings. So for example, if one satellite is in this direction, but it still can be received by here because it can be reflected by something like this. So finally you can receive it, but this is going to be crazy. So for example, if the signal is like reflective by several times, it means the error will be like several times, like 1 to 200 meters maybe. So those are called the signal, the multipass effects. So in majority of the case, if you are in the urban chaos, you can only receive the signals from several satellites with very high elevation angles. Like, okay, so this okay, horizontal, okay, this direction, this angle is like elevation angle. So in this case, the number of satellites, the healthy satellites without the signal reflection is quite limited. Okay, so this will cause the poor satellite geometry. It means like poor satellite geometry means majority of the satellite is received in a very small area. So what we expect is that those satellites are uniformly distributed in the 360 degrees and also from 0 to 90 degrees of elevation. So this will cause the poor geometry. So in short, inclusion in this slide, I want to say, so we have the multipass and also the error signal. So this will cause the poor geometry's measurement quality. So for example, if the in the open sky, okay, the measurement quality may be like, the bass or noise is around like centimeter level. So if the signal is reflected by the buildings, the error of the range can reach around 100 meters. So this is the challenge. So because you only receive very limited number of satellites, as a result, you have the poor satellite geometry as well. So this is for this one. Okay, so after the background, let's look into the overview of the GPS. So, okay, satellite navigation system consists of 3 segments. So the first one is the control segments. So command like infrequent small maneuvers. For example, okay, this is a user segment. For example, this is smartphones. Okay. For example, I am the users. Okay, Dr. Wen, I take smartphones for positions, right? So the satellites, running, okay, with a certain orbital trajectory. So do you think this is good enough? Of course not. So as we mentioned, previously mentioned that the trajectory, the position of the satellite, this is the known variables. So how to achieve this? So this is achieved by the control segment station. Actually, so for example, I define a trajectory for the satellite to follow, okay, from coming to us. So usually, so how to define this trajectory and how to send the trajectory information to a satellite. Okay, this is based on the control segment. Okay, so it means the role of the control segment is to do the communication between the control segment and the satellite. So for example, if something wrong with the satellite, for example, another functionality of the control segment is to monitor the healthy condition of the satellite. For example, like in July, I mean, more than 20 of the Beidou satellite get failed for more than 20 minutes. But majority of people don't know this. But we know because we are working on the satellite. Like more than 20 of the satellite, they like just transmit some unhealthy measurement, some very strange message. So I mean the solution for this is that the control segment station just communicate with satellite to close the signal transmission. Otherwise, it's going to be crazy, okay? Because a lot of applications relies on the GPS, For example, like shipment, I mean the navigation of the shipment, the industry, and for the high-speed trains, for different applications, it relies on the GPS. Okay, so I mean the role of this one is like to monitor health conditions of the satellites and also do some regular communications. Okay, so as I mentioned, like for GPS, we have around like 31, maybe currently we have 34 satellites for the GPS. And from user segment, okay, we have antennas. So antennas is to receive the signals, the radio signals from satellite. Okay, so this is the first part. This is the antennas. So the AD converters is to transfer the analog signals to the digital signals. So and the last one, okay, the very last one is the signal processing. So for example, how to the radio signals from satellite, how to transfer the radio signals to the physically understandable measurements. So for example, like what is the measurements, the range measurement from satellite to receivers. So how to do this is achieved by the signal processing process. So in this course, we are going to focus on, okay, so if we get the range measurement from satellite to receivers based on the signal processing module, so how to do the positioning. So the problem is like, if you know the satellite's position, if you also know the range from satellite to receivers, so how to calculate the location of the receivers, I mean the smartphones. So this is the positioning algorithm. Okay, this is the essence of the positioning algorithm. It's focused on. So, okay, any questions for this page? I mean, in the coming course for the GPS of the satellite navigation, we are going to focus on the positioning algorithm. But also we are going to talk about how to calculate the velocity of the user, okay, based on the GPS measurement. Okay, so this is for the space segment. Like for example, we have around like let's say the very perfect design in 1970. Okay, I mean the US, especially the Jewish lab in Stanford, like designed satellite system in 1990, but it still works until now. Okay, so for example, like July of the year, around like 20 more satellites get failed for the GPS. Such kind of scenario, such kind of cases like lots of satellites get failed simultaneously. So for example, like so one of my friends in Tsinghua University, they did the BDS3, okay, BDS3, the Beidou 3. So the I mean the design of the GPS in 1970s, they are really smart. Because, for example, like currently we have the supply system structure architecture still learned from the GPS in 1970. For example, okay, so the reality like I mean after the direction of the satellite, they can measure at anywhere in the universe. You can receive at least 8 satellites. at the same time. Price is already good enough to do positions, right? So the second position, you need to calculate x, y, together with the crop box. Okay, we mentioned last week. So both positions is good enough. It means it's fine enough for you to do a position. You see that possible in 1970s. It's in 1970, okay. Almost never changed until then, okay. So currently we have BDS from China, okay. The architecture is kind of similar, learn from GPS. Okay, so mentions that attitude increase inclination, okay. The sequence check each day. But means they have some minor change based on the stations previously. So conjunction we are the the trajectory information of the satellite to do next some change if necessary. Okay, so make sure the satellite can safely predefined trajectory for each day. So that's why the satellite position is a non-variable for time. At each second, the trajectory of our satellite is a non-variable. Okay, so it will for segments. So for example, for just segments, we have several. This let's see in Hawaii. Okay, so this part should be California, maybe. So it a lot of stations congested to monitor the health conditions of the satellites. So you to align the time clock errors with the congestion. The role of the congestion is to monitor the trajectory, monitor optical information, and the health condition of the satellites. So this is the role of the congestion segment. Okay, so let's brief for 5 minutes. So how many of you have taken the laptop today? Hands up. Laptop. So how many of you have the Windows laptop today? Installed with Windows operation system. Okay. Okay, that's great. Today we are going to have a like the small example, okay, based on the VS Code, okay. You need to install very small editors, okay, to compile or to run the code based on Python, okay. So Chenjun, have you taken your laptop? No? Okay, if you wish, you can try my laptop if you wish later. Okay, I can contribute to one laptop if you wish. Yeah. So, okay, let's go back, okay? So today, later on, I'm going to introduce one of the one of the algorithm that I love most. I mean, so before when I was a graduate, I mean when I was an undergraduate, so I also learned from the lectures. They say, okay, so let's see, it's the gradient descent. This is the Gaussian-Newton algorithm. So those algorithms, they say, okay, so this is very powerful. You can enjoy today's convenience from smartphones, from your computers. It's all, I mean, originated from those algorithms. But at that stage, I cannot understand. So for example, what is gradient descent? Okay, they say, okay, you need to calculate the partial differentials and then you can do the gradient descent to do blah, 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 blah. But I still cannot understand. So behind those equations, so why, so what is the role and what's the contribution for those algorithms? So because I would say at that time, because the teachers, they did not provide the examples. So that's why from this course, I try to provide the Python examples like to help you to understand, okay, well, the reason behind this gradient descent, why it is powerful to solve some mathematical problems. So for example, later we are going to talk about, for example, if you have like more than 20 satellites, you are going to have more than 20 equations. So how can you like solve like more than 20 equations efficiently, okay? So if you solve the equations by your hand, okay, you cannot finish it in 3 hours. So that's why the gradient descent, I mean, the algorithm we are going to talk about in this lecture is quite, you can have a good sense of the beauty of those algorithms later on, okay, with the Python code. And also you can adjust the parameters, okay, get the sense of how those algorithms will change, okay. So let's go back to this part, okay, for because just now we have mentioned the control segments, and in here, let's see, going to talk about the user segments. So actually for this one, we have already talked a little bit in the last lecture, but still I want to emphasize is like for the typical receivers, we have 3 different levels. Okay, for the smartphone, like it's the most low cost level. Let's say it's like the commercial level. Okay, let's say maybe for the cars, for drones, and this one is for a genetic level. Okay, for example, like in polio, we have the ASGI, land space and genetic information something. Okay, we have ASGI departments. They working a lot on the genetic level receivers. Okay, for the genetic applications. So for example, like usually, for example, if you want to really do the positioning, okay, so first you need to have antennas, right? Okay, you can put the antennas to the outside the windows to collect the satellite measurements, right? So then you need to have a front ends. So front ends is going to be do the signal acquisition and tracking. So to get to like transfer, this is going to transfer the radio signal from the satellite. Okay, transfer this into the physical understandable measurements. I mean the range, the distance from satellite to receivers. So finally, those data will be processed with maybe with a computer or with microelectronics. So to calculate your position. So currently, all those 3 components are combined into a single chips. Okay, like this green now. So this can directly, I mean, this already combine the three components. So one more thing I want to share is that, like actually from like the GP from the BDI Beidou satellite system. So the first version of the receivers, okay, to do the positioning based on the Beidou satellite. So it's, I mean, the first version of the prototype machines in Tsinghua University. I mean, the size is like maybe like this. Okay, it's a big size. It's in big size because it includes the front end and also antennas and the calculation resources, the calculation devices. So this is the overview of the receivers. So the architecture of the GPS software-defined receiver. So I'm not going to dig into this one, but I'm going to quickly go through. So for example, we have the signal will go through the antennas, right? So for example, okay, if we put the antennas to the ortho scenarios, we can receive signals from the satellite, okay, based on the antennas. So the front end, we are going to do the signal acquisition to check the signals from the satellite, and the AD converter is going to transfer from analog to the digital signals, and we can do acquisition checking, and finally to get the navigation data. Navigation data is, the satellite position, the position of the satellite, and some information related to the satellite clock bus. This is so-called the navigation data, NAV. So this is also transmitted from the satellite. So also we can, based on this information, we can calculate the satellite position. So SV means the satellite. Satellite position, if the satellite position is a known variables, right? Based on the navigation, okay, navigation data transmitted from the satellite. And also the range, the distance from the satellite to receivers, okay? This is also received from satellite. You can do the position calculation, okay, based on more than 4 satellites, you can calculate your locations. So this is roughly the whole pipelines. So you don't need to really dig into those components. Maybe for this one, it's already a course. Okay, this is a course. Okay, this is for today's course. So for example, for acquisition, it's going to be determine the visible satellites, the cost values of the carrier frequency, and the code delay. So the code delay, okay. So how the range is obtained? The range between the satellite to receiver is obtained by the time differences between the signal transmissions, right, from satellite to receivers. So this is called delay. The range is equivalent to the code delay. So the carrier phase, okay, the carrier frequency. So this is another measurement. Okay, we are going to mention this in the next week. So this is used for the real-time kinematic positioning. The carrier phase. So for today's lecture, we are only use the code delay, okay, this measurement to do the single point positioning. So for the tracking process, for the tracking module, it's going to refine these values and keep track and demodulate the navigation data from satellite, okay? So refine these values to refine those code delay and carrier frequency. And keep track and demodulate the navigation data means to demodulate means to decode the data of the satellite position. Okay, and okay, let's run navigation data decode. For example, to get the shoulder range, GPS time, blah blah. Those things are all based on the first two modules. So based on this, you can get the measurements from the satellite and finally do the position calculation. Okay, so this is roughly the idea behind this GPS receiver architecture. So in this lecture, we are going to focus on this position calculation. Okay, and the satellite position, this is the known variables. You can directly decode from this navigation data. Okay, satellite navigation data. So for the user position, okay, let's to calculate the receiver position through the estimation technique. The gradient descent or the least square process, okay, in the coming slide. So what is the signal acquisition? So for example, like if I receive a radio signal, how can I identify this is from satellite? Okay, so this is a simple explanation for the acquisition process. So for example, from satellite, so lots of satellite in the sky. So which is from satellite? So which is from GPS or which is from GLONASS? So how to identify? So this is the role of the signal acquisition. So acquisition process is going to do this. So for example, basically the peak. Okay, acquisition process is to aggregate different radio signals from the sky with different signal strengths. So finally, you're going to find a peak. So the peak represents one of the satellites. So this is roughly the idea of the acquisition process. So the checking is to continuously check the color phase and Doppler frequency of the GPS measurement. So loop filter is used in the tracking loop. So actually for GPS, we have three different kind of measurements. So the first one is the time differences between the satellite receivers. Okay, I mean the signal transmission. So this is called code delay. Okay, so this can provide a range between the satellite receivers. So the second kind of measurement is called phase. The code phase. The phase is provided especially for a real-time kinematic. This is kind of similar to the range measurement, but additionally there is one more additional variables to be unknown, to be estimated. So later we are going to have equations. So the last one is the Doppler frequency, because I mean the satellite is moving, right? If I mean the relative velocity between the satellite and the user is zero, so there's going to be no Doppler shift. So because the relative motion, I mean for a signal transmitted from the satellite, because of the motion differences, they will lead to a Doppler shift. Okay, so later in the next lecture we are going to talk about the Doppler shift. So this can be used to infer the velocity of the users. So the first two kinds of measurement, okay, the code and the phase, okay, this can be used for positioning purpose. So for the Doppler frequency shift, okay, this can be used to infer the velocity of the users. Okay, velocity can be obtained from the Doppler frequency measurement. So this is, directly associated with the velocity of the users and satellite. So for the code and the phase measurement, okay, so this is associated with the position of the receivers. So for example, the Doppler frequencies, the typical values is like this. The code frequency is kind of like this. If you multiply the speed of light, you're going to get the distance. Okay, so let's look into the base principle. So in the very first lecture, we will talk a little bit about the theory of the GPS. So let's recap this quickly. So for example, this is a satellite, right? The position of the satellite, this is the known variables. Okay, the position of the satellite, this is a known variable. So and also the distance from the satellite to the receivers, this is also known variables. So for each of the satellite, okay, we can draw a circle, okay, based on the position of the satellite and the range, distance, okay. So there is the intersection point. So the intersection point is actually corresponding to the location of the receiver. Okay, the intersection point is corresponding to the location of the receivers. Okay, so the principle, okay, this process is called triangulation. So the principle of the satellite positioning is based on the triangulation process. Okay. So as I mentioned, okay, the GPS positioning is based on the triangulation method, and no information obtained from the signal processing is, the position of the satellite. Okay, the position of the satellite is a known variable, and the distance between the satellite and the receiver, this is called code measurement, or you can call it code delay, code measurement. So another name is like shoot range. Okay, it's equivalent. Code measurement or shoot range measurement, this is the same. Okay, this represents the distance from the satellite to the receiver. Okay, this is calculated based on the time differences. For example, the satellite signal is transmitted at T1, okay, and finally it is received by the receivers at T2. So the time difference is multiply the speed of the light. So this is the distance from the satellite to the receiver. So this is called the shoot range. So it's make up by the two parts. Range is the distance, right? So the shoot means this is not the real value. So this is because the range also includes some errors. That's why it's called shoot range. Okay, you can this shoot range. So range means the distance. Shoot means this is not the accurate model because some errors are included in the range. So for example, the clock bars. So how to understand? Okay, so for example, if we calculate the time differences, like if the signal is transmitted from the satellite at the T1, and finally you receive a signal at T2. So the delay is calculated by T2 minus T1, right? Multiply the speed of the light. So this is the distance from satellite to receivers, right? So this is correct based on the assumption that the clock between the satellite clock and the receiver clock is fully aligned. So for example, if you use the smartwatch, okay, the mechanical watch, I mean the clock is going to be drift over time, right? It's the same. I mean for the receivers, the clock will also drift. It means after several days, the clock of the smartphones and the satellites are not well aligned. Okay, in this case, there's a clock differences. Okay, so that's why we call this is a shoulder range. Okay, later we are going to have an equation to show this. So how many satellites are received to obtain the 3D dimension of a receiver? I mean, this is the ideal case. Okay, the ideal case means there's no errors, there's no clock bias, there's no clock errors. So you can get a unique intersection point. But the practical cases is like there's a clock differences. Also need to estimate or need to calculate. So in this case, you need to estimate 4 unknown variables, x, y, z, together with the clock errors. Okay, sometimes we call it clock errors, clock bias. So in this case, you need to estimate 4 different variables. You need 4 different satellites, okay, to calculate the position of a receiver. Okay, 4 satellites are required to achieve this, okay? So let's look into the shoulder range measurement. So actually, this equation is like you can understand like actually we have 3 clocks. I'm not going to say, for example, okay, I say this is much easier to understand. So we have a satellite, right? Okay, let's say satellite. They have a clock. Okay, if the signal is transmitted at T1, and finally the signal is received by this receiver, okay, at T2. So the speed of the light multiply T2 minus T1. This is the distance between the satellite to receivers, right? This is based on the assumptions that the clock is fully accurate. They are fully well aligned. But the case is that there is an error, okay? There is an error between the clock of 2 different clocks. So in this case, you have error terms. So C is the speed of the light. This is the time differences. And this one is the clock differences between the satellite and the users. So in this case, okay, this is the known variables, and this one is unknown because we don't know what is the errors, what is the clock errors differences between, the clock in the satellite and the clock in the user side. So in this case, we need to estimate this simultaneously. So the user clock errors also need to estimate it. Okay, this is corresponding to this as explanation. So in this case, if you look into the equations, okay. So for example, this is 3 different satellites, right? 1, 2, 3, okay. If the satellite, okay, it's not if the satellite position of the satellite is known variables of this satellite, okay, the position is a known variables, and also for this one, and the range, this is the shoulder range. This is received from the GPS signals, right? You can decode range, okay, maybe like several thousands of kilometers. Okay, this range is known variable. So what we want to estimate is XYZ. So XYZ is the position of the satellite. Oh, sorry, position of the receiver. Okay. So what you want to estimate the position of the receiver. So because we have the clock errors, okay, sometimes it's called receiver clock offset. So it means we need to estimate XYZ. Okay, and okay, in this slide, okay, the red color, okay, represents the unknown variables. The blue color represents the blue and black color represents the known variables. So it means 4 satellites are required to do the positionings, right? So it's clear at this stage. So for example, this is a example of the satellite. So for example, if I just I stay in the roof of this building, I continuously receive the signals from satellite, maybe like 98. Okay, a specific satellite. So the range will change over time. For example, like this. So this is why. For example, I just stay static on the roof of this building. I receive the signals from should range from the satellite 98, but the range will change over time. Is that correct? So why? This is because the satellite is moving, right? Because you're static, but the satellite is moving. But the great thing is that all the satellite is moving. The position of the satellite is non-variable. Okay, so I mean, for example, this is the time, this is distance. Like for example, like this is 20K, okay, 20,000 kilometers of this distance. Okay, this is 3 different satellites. You can see that it will change over time. Okay, it will change over time. So this is the reason. So the variation of the shoot range. So the shoot range, okay, this is the measurement of the distance you receive from satellite. So mainly due to the satellite motion and the Earth's rotation, because the Earth will also rotate. Okay, so this gap is because there's an additional error from the clock bus. Okay, so this is roughly the shoot range. Of course, I mean the signal from satellite, okay, goes through the sky and finally receives by the receivers. We have some errors. So the errors coming from several components. So the first one is from satellite. So for example, the satellite orbits. So because we know the satellite location, this is a non-variable. So this is estimated by the, for example, based on the control stations to do the monitoring. But still, the position of a satellite is still includes some errors, but it's very minor, like within like half a meter something. Okay, so the first error is from the satellite orbit. So the satellite clock, I mean, although the satellite clock is an atomic clock, but still some errors included, but it's quite minor, still quite minor, maybe like 0.1 something, okay, 0.1 meters in range, by range, okay, represented by range. And also there are some very minor errors like the satellite phase center, wind up, signal bars. So actually, I mean, if we use the real-time kinematic technique, okay, all those errors can be eliminated, okay, can be removed in the, okay, we are going to mention this in the next lecture. So roughly, I mean, the error sources coming from the satellite-wise, okay, it's around like 1 to 2 meters, 1 to 2 meters from satellite-wise. And all those error terms can be modeled, for example, with some physical models, okay, predefined model, pre-investigated models to model errors. So for example, like the satellite clock, okay, this error also subject to some physical models. You can model, for example, exact error is 1 meters. We can, based on some functions, we can calculate the error is like 0.9. It means you still have a gap, okay, 0.1 meters. So still, I mean, those errors coming from the satellite wise is around 1 to 2 meters in summation, okay, in short. So this is the error sources from the satellites, from the satellite wise. So the second one is coming from the transmission related errors, like the transmission delay. So for example, we can have some ionospheric delay and the tropospheric delay. So this is easiest to understand. So for example, this is like roughly around like around 60 to 1,000 kilometers above the Earth's surface. So this is the, okay, ionospheric delay around like 10 meters. But the good thing is still, okay, so those errors can be modeled, okay, with some physical models. So in this case, I mean, for example, the exact errors can be reduced to around 1 to 2 meters, 1 to 2 meters based on some existing physical models. Okay, so okay, in the week 5, we are going to have tutorials for GPS positions, right? So later we are going to have some example values for those errors. Okay, from the tutorial you can have a better understanding of those values. Also, we have the, like, if the signal transmit to the ground, okay, if there are some buildings, we have some reflections. In this case, we are going to have some errors in your measurements. So this is called the multipass effect. And the Earth's rotation, so this can be compensated. Okay, no worries. This can be compensated because we already know the velocity of the Earth's rotations, right? So in this case, we can compensate this part. Okay, we can compensate this part. Okay, this error turns can be removed. So from the receiver side, okay, so this is from the sky, right? This is from the satellite wise. The last part is from the receiver side. So receivers, they also from, as you mentioned, okay, from user side, we have 3 different levels of receivers, like the smartphone level and the commercial level and the GTEC level. And for different levels of receivers, they have different errors or different noises. So roughly the noises coming from receiver is around like several meters. Okay, so based on the different levels. So for example, if you use the GTEC levels, the accuracy of a receiver should be great. Okay, so this is for the errors from different sources. Okay, so this page is very important. Okay. Okay, your attention. Okay, 1 to 2 minutes, maybe. Okay, so this is the should range measurement. So if you look into the whole positioning problem, okay, it's like XYZ together with the clock errors, right? So this is the unknown variables. So this is the typical measurement models. Measurement model is a should range. So for example, okay, so this is the should range. So for example, how to understand this one? So for example, if you use a receiver, it will receive a measurement from a satellite. So with a given transmission delay. For example, satellite signal is transmitted from T1, and finally you receive a signal at T2. Right? This time differences multiply the speed of the light. So this is the distance. But the bad news is this distance includes several error turns. So if there's no clock differences, no clock errors, left side should be equivalent to the distance, right? There's no more left side, right side, okay? The should range should be equivalent to a range distance if the clock is, 100% perfectly aligned. Is that correct? There's no right size. So if there are some clock errors from satellite, okay, this is the clock errors multiply the speed of the light. This errors includes the 2 terms. This S means the satellite clock error. This is the receiver clock error. But the good thing is this is a known variable. From the satellite wise, all the variables is known. This satellite errors, satellite clock errors, this is known variables. This is the receiver clock errors. So in here, okay, so the S means the index of the satellite. So R means the receivers and T means the timestamps. Okay, so because we also have the chop-spheric delays and interspheric, okay, reverse. We have the chop-spheric delays. Okay, we have 2 additional error terms, right? Okay, so this is the Gaussian noise. Okay, to represent some receiver noise or some multipass noise. So in this case, so again, if there's no error turns from clock, okay, if there's no error turns from clock, okay, the left side is the should range. Okay, the should range is coming from the time differences of the signal transmission multiply the speed of the light. So this one should be equivalent to this range distance, right? So because of the clock differences, we have additional terms in here. And also this is from the chop-spheric delay and interspheric delay. So this is the Gaussian noise to represent the noise coming from the receiver thermal noise or some multipass effects. So in this case, in this equations, this is a known variable, okay? And this range distance includes the receiver's location. Okay, later we are going to have details. So let's make a conclusion for this page, okay? So the left side is the should range. Okay, so this is obtained based on the time differences between the signal transmission and multiply the speed of the light. So the right side is the range distance. So this can be calculated or modeled directly based on receiver location and the satellite locations. And this is because the clock differences, and this one is because the transpheric delay and innospheric delay. So as we mentioned previously, this and this can be modeled directly with some physical models. For example, based on the satellite information, we can get this value. So it means finally in this equation, okay, the unknown variable is the receiver clock error. Okay, this the unknown variable. This is the unknown variables. This is the known variables. So the Gaussian noise, we can just assume some weightings. So I mean, this one is also known variables. And also this is a measurement, okay, received from the satellite. This is also known variables. It means the only unknown is this one. And also XYZ is included in this equation. Okay, so XYZ is included in the range distance. Okay, which means 3 unknowns in here and 1 unknown in here. For one equations, for one satellite measurement, we have 3 plus 1 unknown variables. Okay, this is the same. Okay, this is exactly the same as previous page. Okay, this is exactly the same. So as we mentioned, the blue one is the, I mean, in this slide. Okay, so the blue and black represents the known variables, and the red part represents the unknown variables. Okay, so at least this is the unknown variables, right? The satellite positions. Okay, for example, the T means the timestamps, and S means the satellite. Okay, X, Y, Z represents the position of the satellite. Position of the satellite S at timestamp T, and receiver position represented by this one. Okay, receiver R, T, X, Y, Z. So this is the unknown variables, right? And the geodetic distance, this can be represented by this equations, right? Because the square distance between the satellite to the receivers can be calculated by the two positions, right? So in this case, if you look back to this equations, okay, known variables, and also the known variables, right? The satellite clock, this is also a known variables, right? So in this range distance, the satellite position is a known variables. The only unknown is the position of the receivers. It means this position variables XYZ is associated with this measurement equations. It means in this equations we have 3 plus 1 unknowns, 4 unknowns. It means to solve the 4 variables, we need to receive 4 different measurements. 4 equations, 4 unknown variables, we can solve it. So this is roughly the idea. So any questions? So for example, okay, in here we have a square roots. It means let's will introduce the nonlinearities because this is the nonlinear components. So in this case, for example, if we get 4 equations, you still can solve it. Maybe if you are strong in mathematics, you can still solve it. If you get 20 satellites, if you get 20 measurements, it's hard to solve it. So this is a challenge. So in this case, if we get at least 4 equations from 4 satellites, one satellite is going to be contribute to 1 measurement, okay? 1 equations. It means if you get 4 satellites, you can solve the equations efficiently, okay? So if you get 1 more satellite, maybe 5 satellites, you get some redundancy, okay? So that's why we need to introduce the procedure to solve it with the gradient descent, okay? Okay, this is the known variables. This is the tropospheric delay, and usually this is around like 2 to 3 meters, 2 to 3 meters. So this is roughly the values. Okay, I think this is like the simplified version is quite easy to understand at this stage, right? So for example, this is the range. Okay, we can have the square root distance plus the b. So the B here is the combination. The B is the combination of all those components. If you combine all those parts to the B, and this is the square root distance, right? So in this case, we can get this simplified equations. So the B, this is the square root distance, right? This is the shoot range. So Sn is the satellite. Ns means satellite. 3 means the index. So Rt. So in this case, this is the square root distance. This B includes the combination of all different components. Combine all those components into the B, okay? So we can have a simplified equations. So this is much easier to understand, right? So this is B. So in this case, okay, if we get 4 equations, right? So you can solve it, okay, as I just mentioned, based on what you have learned from high school. So if you get 20 equations, we cannot solve it directly. So mathematically, we are going to do the linearization by the Taylor expansion, and with a linear least square process to solve x, y, z together with the B. So actually, the B is it's more like a middle variable. I mean, to solve the x, y, z is our objectives, right? So B is like it's a if you want to solve x, y, z, we need to calculate the B as well. It's more like a middle variables. Okay, so take break for 5 minutes. Okay, so let's go back. Okay, I try to finish this lecture around like 6:10. So so as you just mentioned, if you have like 1, 2, 3, 4 questions, you can solve it. Okay, based on what you have learned from high school. But still, if you get like 10 to 20 satellite measurements, okay, you need to solve like more than 20 equations. It's almost impossible. So that's why we need to use the linear least square estimation problem. So any of you have ever learn about the linear least square estimation from maybe from some elective from computer science? Ever learned this before? Least square estimation? No. So actually, I just mentioned like a gradient descent. This is a very beautiful algorithms to solve the complex problem efficiently. So even the problem is a nonlinear equation, it still can solve it by doing the linearization process. Okay, so we call the Taylor expansion. So okay, let's recap this question. So the question is that if the number, okay, the ALC is a linear least square estimation. Okay, so if the number of the question is equivalent to the number of the unknown variables, okay, the matrix solving method can be used to directly to calculate a unique solution. So it means that like you directly have 4 equations, you can solve it. Okay, with you can write the equations in the matrix form. Right? You mentioned in the first lecture. So if the number of the equations is greater than the number of the unknown variables, so the linear least square error can be adopted to calculate the optimal solution. So this is the case we want to talk about. I mean, the cases is like you get several more equations, you need to solve it. So we are going to use the linear least square estimation. So okay, so again, the Kepler problem is like we have x, y, z, b. So how to solve it? Okay, get multiple satellite measurement. So to start with the linear least square estimation method, I'm going to have a quick overview. Okay, about how this algorithm is developed in the past several hundred years before. So first, okay, so the linear least square estimation is the linear square approximation of the linear functions of the data. So the most, the typical cases is the line fittings. So for example, in the statistics lecture, maybe in the U1 or U2, if you learn the statistics, so you may have examples like, so how to evaluate the standard deviation of the line fitting problem. So for example, if you get multiple lines, so how to evaluate the standard deviation of those points with respect to a fitted line. So you may learn this before. There are two primary categories of least squares methods problems: the ordinary and the linear square and nonlinear cases. So in this course, we are mainly talk about the linear least square and the nonlinear least square. So essentially, this is achieved by the minimization of the sum of the errors of the square residuals. So for example, in the line fitting problem, okay, so the principle is to find a line that fits most, okay, fit based with those points, right? So how to evaluate it is good. So we can calculate the distance from the points to the lines, right? So this is what we learn from the statistics. So basically, this is the idea behind this line fitting. You try to evaluate the distance from this point to the fitted lines. Okay, so this is generally the definitions. Of course, we have a very long history. I mean, in terms of the developments of this least square estimation problem. So before, for example, we have researchers first in 19, for example, like before they try to observe the trajectory of some stars. But I mean, the case is like occasionally they can observe some position of the stars. But the problem is that those measurements are not continuous. So how to estimate or calculate the location of the stars based on those uncontinuous observations of those stars. So the idea is like this is more like the data fitting problem. For example, okay, if I want to get this line, but I get a series of measurements, those discrete measurements. So how to get this line function? So this is more like a fitting problem. So previously, when I wish to a very interesting. So currently, I mean, we have very famous solver. Okay, we have very famous solver. So this is, I mean, the solver is open sourced by Google. So this is developed by Google specifically to solve the nonlinear least square estimation problem. So the name of the solver is called Ceres. Okay, this is to memorize the story. Okay, memorize the story to observe the stars. So for example, like at the beginning, so in 181801, okay, find name the stars as the Ceres. So as I mentioned, the Ceres currently is one of the based solver, I mean open source solver. So for example, I just show you the solver. So let's see the Ceres solver, okay? So name, you see the name is exactly the same. So the Ceres solver, this is developed by Google. So this is an open source C++ library for the modeling and solving large-scale complicated optimization problems with a least square estimation. So this name is exactly the same as this one. Exactly the same as this one. So for example, like in over months, I mean, finally they observed several measurements from the stars. Okay, for example, based on several measurements, we can use so the Gauss, okay, Gaussian-Newton Gauss process. So the least square method. So the least square method is just the same as the AISC we mentioned in the previous page to calculate the position of the stars. So this is the old stories like presenting, elaborating how this concept or this algorithm originated from. So after that, they do some continuous work. So for example, find in like 1770 Laplace, okay, Laplace transform, Laplace, they propose this minimization function. So for example, like if we have a series of observations, so how to define the error function to solve it efficiently. So this is roughly the story. So in the old stage, they first define the concept of the average. So for example, if I have I try to measure the distance from me to the walls, I get several measurements. So the basic concept is to do the average. Okay, do the average to get the distance. So this is the most straightforward concept. So after that, so for example, if this distance is not less straightforward, okay, we need to define the cost function or the minimization function to solve it. Okay, so this is roughly the concept. So several, I mean, properties for the AIC. So for the first one, okay, the linear least square estimation means the function need to be linear. So for example, like if the x is unknowns, so in here, okay, this is the linear function because there's no square. For example, there's square roots or some squares. That's going to be the nonlinear functions. So the first assumption is that the problem is a linear case. So the second one is like, for example, like for the observation, for each of the observation, they should be independent. So for example, like how to understand the independent, it means for example, like the satellite measurements. For example, we have like 20 satellites. We have assumptions that all the measurement from different satellites, they are independent with each other. So in this case, when we calculate the least square estimation problem, it's going to be straightforward. I mean, each of the measurement are not correlated with each other. Okay, because they are independent. So you not really need to understand, okay, well, how to calculate the independence, but what you need to understand is like, you first need rest on this strong assumption, okay, the problem is a linear case. I mean, for example, x is unknowns, so they have this linear correlation, so y should be equivalent to a multiply x plus the noise. So this is the basic assumptions for the linearity. So another one is like, for example, the Gaussian noise, and for example, for error terms, they should have the constant Variance means how much you can trust in a given measurement. It's like the standard deviation. You can understand this is the uncertainty of the measurements. So for example, this one is like basically we require the measurement noise should be subject to the Gaussian noise. This is to say, okay, all the measurements should have a predefined uncertainties. Okay, so those are just some general concept, okay? Lots of applications. So for example, like today, I mean, like AI is quite hot, right? So for example, when we have a large scale data set, okay, based on the networks, we need to train a model. So the training of the model is like, so this process is a estimation process. So I mean, the training process, I mean, the computer is using the GPU to solve the gradient descent problem. So for example, application of the least square in, okay, so LSC means linear least square. Okay, least square. So provides a way to model the, for example, a data fitting problem. So giving a series of data. So how to get the curves, I mean the lines corresponding to the basic fits of this point. So the noise filtering and also prediction. So for example, we have some history data, so we can predict how the future of the data will looks like. And this one is like deep learning. Okay, we can do the inference. So based on series of data, you can train networks. So the training of the network, the process is it's like solving a gradient descent problem. Okay, solving a gradient descent problem. So those are the applications. So in fact, I mean, for the GPS problem, it's more like GPS position problem. It's more like a data fitting problem. Okay, later I'm going to show this. So for example, let's first look into the line fitting problem. Okay, based on the linear least square problem. So for example, if this is a line and we provide a series of points, so for example, the purpose is to find the best fit line from a set of points which have a minimum sum of square residuals. So the residuals means the errors. So for example, have a series of points. So the distance, I mean, from a point to this line, this is called residuals. Okay, you can call it errors as well. So data points, for example, we provide a series points. Okay, 2-dimension. Okay, x1, y1. Okay, a lot of points placed in different locations. And also this assumption, okay, this assumption is based on the independence. So we assume that all the points are independent with each other. Okay, so let's say it's based on the independence. So basically those assumptions are like normally are used in majority of applications. And for the output, so I mean, this is the function you want to fit, right? For example, we want to fit this function. So to determine this function, we need to have the a and b, right? X, y is the points. I mean, this is the points provided points. So a and b, the red part is the unknown variables we want to estimate, right? So it means again, so in short, in this slide, we want to say x point, okay, x, y, those points are the known variables. So what I want to obtain is a and b. So those are unknown variables by doing this fitting, okay? This is what I want to know. So again, I mean, in the coming slide, a and b and x, y are known variables. So a and b range are the unknown variables, okay? The same. So first, okay, so I mean, how to calculate the N and B based on a series of data. So design the target residual, as we mentioned, the residual can be calculated from this point, okay? This, I mean, the perpendicular distance from this point to this one, okay? We calculated by this value and this value. So now is the we have two kinds of the residual. It means we vertical to get the distance, okay, this distance. So the points locations are known variables. We want to find a line, we want to find a straight line with specific those points. So for each lines, it can be determined by a and b. So based on the AB function, so we can calculate the errors. So the errors. So for example, this distance can be calculated by y minus this function, this point, given x1, so the y is represented by this components, right? So this is the distance corresponding to this part, right? So the residuals, the differences between the two parts. Okay, the distance between the two parts, this is so-called the residuals. Okay, you can also call this is the error. You can also call this is the residuals. Okay, so in this case, the residuals is corresponding to the distance between the targeted line function and the data points. So this is the line function, okay, and the data points. This is the residual, okay. So this term is very important. Okay, we are going to repeat this term for many times in the coming slide about the satellite position. Okay, residuals is corresponding to the distance between the data points and the points and the values of this line. So what I want to say is in this function, okay, in this residual, a and b is unknown variables. So we try to get the base fit of this line. Try to find the base a and b to minimize these functions, right? For example, if this distance is all 0, it means this is the base fit. Well, I mean, unfortunately, this is impossible because we have a lot of noisy points. We are only trying to find a point, find a line with minimize the distance between the line and the points. So this is the idea. So for example, if we get the points from multiple lines, we can get multiple residuals, right? So previously we defined a distance from one point, okay? Define a distance from one point to the lines. Okay, if we combine the distance from multiple lines, we are going to get a residuals, right? AXB minus Y, AXB minus Y2. Okay, this is the distance from multiple points. So this, I mean, again, so this is the vertical offset because this distance can be calculated by this. This is the vertical distance. This can also calculated by the perpendicular distance from this point to this one. Okay, so this is the vertical offset first. So in this case, we can, as we mentioned previously, so the objective of fitting this line is try to find the base A and B representing the line with the minimized distance summation. So the summation of all those distances can be represented like this. So the summation of all the distance can be represented by this, right? So this is called residuals. And this cost function, so this residual function is the summation of all the error terms, right? All the residuals, right? So if you can understand this concept, it's really important because in the coming problems, it's exactly the same. So this is called residuals, and this is the summation of the residuals. And this is called, okay, this function, you can call this function as the cost function. So for example, if all the points are exactly located in a line, this value should be equal to 0, right? But because because the points are not 100% located in the lines, if all those points are perfectly located in the lines, the error function should be equivalent to 0, right? The ideal case, the practice, this is not exactly located in this one, so we need to try to find the base line corresponding to A and B to represent the line to minimize this value, to minimize this distance. So the problem is that if we get multiple equations, so how to solve it? For example, like if we get n equals to 100, okay? If we get 100 error functions, so how to solve it? How to solve this equation? So let's go back to the basics of the fitting problem, the gradients. So for example, for this, okay, square function, okay? For this square function, the minimized point is of course the bottom of this curve, right? This quadratic function, also you can call it square function. So what is the, what's the key features of this minimized point, okay? For example, if we go back to this this is a square function. This is a quadratic functions, right? D1, D2, D3, blah, blah. This is a quadratic function. So if you want to minimize, so what is the key features of the quadratic function, of the square function? The key features is, the optimal solution, the minimized point, the gradient is 0, right? The gradient means the partial differential values of a given point. So the gradient of this one is like approaching 0, isn't it? So this is the key features. So it means the base solution, for example, go back to this problem. The base solution to calculating A and B is to find the point. Let me make the gradient of this equation to be 0. Okay, so this, the point is like this. So for example, if you have multiple, if you have like multiple variables, okay, so the gradient is going to be into a vector or matrix. So for example, if you have x1, x2, x3, so the partial differential is going to be like this. Okay, it has multiple variables. Okay, so the conclusion I want to say, the gradient approaching 0, usually this point is an optimal solution. So this is a solution to, for example, this one, okay? If we are talking about a 2-dimension quadratic function, okay? If you are talking about, for example, like x squared plus y squared fxy, so this is going to be the function. So, for example, like if this function is f x y equivalent to x squared plus y squared, right? If you want to minimize this function, so usually, basically, the points lead to the 0 gradients. Okay, it's going to be the optimal solution. Okay, so this is essence, the basic principles behind. So for example, to make sure the gradients value vectors, okay, this one equivalent to the partial differential of f with respect to the x, and partial differential with respect to y should be equivalent to 0. Equivalent to 0. So this point is usually the optimal solution point. Okay, so let's go back to our problems. So just now we have already defined. Okay, let's one more time to so so next time you can download the slide from the Blackboard. Okay, so let's go back to, okay, the cost function is like this. Okay, the cost function is like this. So in this cost function, okay, the a and b is unknown variables, the blue one is the known variables, right? Okay, so if you want to calculate the gradients, okay, so if you want to calculate gradients, so the GAB is corresponding to the cost functions, right? So first we do the partial differential with respect to A, because in this function, x and y is the observations, is a series of points, right? A series of points. So the A and B are the unknown variables. So if we do the partial differential, it's going to be like this. Di multiply this one, because we have the d square. For example, like di square. Okay, if you do the partial differential for this one with respect to a, that's going to be 2 multiply di multiply the partial differential of di corresponding to a. It's like this. So this is the partial differential of the square di, and this is the partial differential principle. So in this case, di is this one, and the partial differential for this one is going to be xi, the partial differential for a. Okay, so this one is corresponding to xi, and di is equivalent to this. So at this moment, it's okay. It's fully okay, right? So for example, also we can calculate the partial differential for the b. Partial differential for the b. So in this case, we can get the partial differential for b. So this is the same. So this is the di. Okay, sorry, this one is di multiply 1, because for this one, if you do the partial differential for b, it's going to equivalent to 1. So it's clear, right? So in this case, you can calculate the partial differentials of those gradients. It's going to be like this. Okay. So for example, as I mentioned, the optimal solution usually lies in the points with 0 gradients, right? with zero gradients. So in this case, we want to make this to be 0. So by solving these equations, you're able to get the A and the B. Theoretically, okay, you should be able to get A and B. So because this is a linear case, you can solve it efficiently. Okay, so let's take a try. So please follow the tutorial. Okay, follow tutorial. So any of you cannot download the slide? So if you cannot download the slide, okay? So try this. If you cannot download slide, please go to this. Please search this repository in the GitHub, okay? So get into this, you should be able to find the slide. So if you search, if you go to this GitHub website, okay, if you go to this GitHub website, you're going to have the lecture notes. Lecture notes here, okay, go to the week 2. We are going to have the 4 slides, okay? So from now, okay, please install this in your computer, okay? Install this in your laptop. So if you wish to have one more laptop, I feel free to, I can contribute one more laptop to you. So Chenjun, you want to try? Yeah, if you wish, you can try this. Okay, get back to your chair if you wish. So yes, so now can you like just you log in the Zoom? I can share the Zoom link, and you can log in the Zoom and share screen to show the process or procedure of the installation. This is the Zoom information again. Log in first and just share a screen to show the procedures. So our TA here will also illustrate the process of installation of this example, okay?
I see the link again.
Oh, yes. Yes, you can share screen. Okay. Send a request. Okay, I just stop sharing so you can share screen. So you can try in your computers and also OTA will like make a demonstration to see how to show like how to install those VS Code and run a demo. Okay. Also, you can try in your laptop. If you wish, you can look into the screen as well. Okay.
Yeah. Okay, so you can download the code from the GitHub page. You can download via the HTTP links or download the zip. And I download the repository to my computer. And this is it. You can unzip it and enter the sample codes. This actually is a profit, and you can enter this document and click your right mouse and open it in your terminal. So so you should install the Python first.
So this is based on the assumption that you already installed Python already.
Yes, this is already installed Python.
Can you uninstall your Python and install Python again?
I can reinstall my Python.
You can just remove your Python environments and just demonstrate one more time from scratch.
Yeah. Okay. If you want to download Python, you can go to the search for Python and it's in its website. You can download the used Python.
So currently the Python is I mean from in this world the Python should be the most popular language in this world currently. It's even more popular than the Java and more popular than Java and C++. So generally the Python is I mean is developed by an engineer from Google. So developed by an engineer from Google. Yes, you can go ahead.
Yeah, once you download the Python setup, you can directly to install it. Use the default option. The default option is conversion everything we use.
So please I mean take a look at the PNP. So this is a case to install additional toolbox. So Python, for example, if you want to install toolbox for machine learning, okay, for example, in the MATLAB, okay, we have a lot of toolbox. So in the Python, for example, if you want to install some new toolbox, like for machine learning, like Scala or Matplotlib, so quickly use the PIP tool. Okay, so please take this one, take the PIP. Yeah, just go ahead.
Yeah, and this Tkin pronunciation.
Yes.
This is for visualization, and we use it in this sample. Okay, then click next. Use the default. Everything is the default. Okay, yes, and wait for its install success. And we can.
So how to check if you have like already installed Python or not? How to check?
I think you can use this. Open your terminal. The terminal is CMD. You can open it by search for the CMD or search for the PowerShell.
So it's already directly about. You need to install a PowerShell.
You don't have to install it. It's in your system.
Okay, for the Windows 10, it's already included.
Yeah.
Okay, that's great.
And you enter the Python and click table.
Okay, for example,
yes. Version is 3.12.6, and then you can open the result. You just download it there and open the sample codes. And right click, open terminal. Then you can use the order Python and enter your enter the code you want to use. In this case, we use the demo line feeding LLSE, which is linear least square estimation. So we can demo. Okay, line feeding linear least square estimation. We can use this and click the enter. And we can see this is the visualization part. You can click points here, and it can generate the fitting line to this window, and you can see how your points, the point you choose, affect the fitting line. And you can see when the coordinates and the line fit function here in your terminal. This is line fitting case.
So what's the number here represents? For example, the function is one. This is A. This is B, right?
Yes.
So what function represents? What's the number here represents?
Points coordinates.
For example, if you add one more point, right?
Yes. If you add one more point, it will show your point coordinates.
Okay. So in this way, the result, for example, if you have like quite a few points, so this line is try to this process is try to find base line to provide the base face with those lines. So this is a linear least square process.
To have the least square process, which will be talked about in the following lecture.
Yes.
So should I demonstrate that?
No, just wait. So I finished the demo in your laptop. I'm going to go through the Python code, okay? To introduce like how this code looks like and the functionality of each line. Code. Okay, copy your code, just copy it. Because you are installed. You already installed it. So have you downloaded the code to the repository. First, you need it says check. So in this photo, you can choose see currently okay, this is the frame. So currently you have installed Python already, right? Okay, we get a string. So you get a GUI here with double creative track define. You already installed this one? You download the whole repository. Then you download the code. Okay, please download the code first. Oh, just this. Here is
the main code is in the fit line. Fit line this last one fit line. I mean the core code. I would see it for realization.
See? Success? Oh, yeah, you're in Windows. And the next. Okay. Okay, here. So it's using a Linux system, so maybe some different. Success? Okay, it's good. Success? Okay, that's great. If your laptop is not, you should have one. Okay. Success? Stop. Success? Okay. Okay, yeah. Page. Okay. Python is the instructor suspension. Okay. This kind of here is not a Python again, it's correctly. Python. Give you a little add. Yeah, I switch. You can receive from Python, for example, like it seems that your Python version is like this. You can receive because, for example, all examples like you need to install a Python as a parameters, so you can just follow the procedure to install a Python. So no worries if you cannot succeed, you just reach out after the course, and if you still cannot do it, you can raise the issue. Or if you cannot finish this lecture, you can just try one more time of the lecture and also can raise the issues from the file. Okay, you can take your laptop. Okay, that's great. It's going to be okay, so okay, it takes 7 minutes to introduce the code, okay? Okay, the code is slide. So as we mentioned, in this code, okay, so for example, so it's going to be like you can solve all the cost functions and get the gradients of the partial differential for A and partial differential for B, right? So by doing this function, okay, that's only one equation, right? By doing functions for this is only one equation, right? It means you only have two equations. So it means you efficiently because this is a linear function. Okay, so you can solve it efficiently by the two linear equations. So if you look into the codes, okay. So of course, I mean the logic of the Python. So in last week, I asked a question like how many of you have learned Python before? At least like 80%, right? So if you any Python, okay, just as I mentioned in the first lecture, you can learn offline, okay, by yourself. Here I think some general for the Python language screen out. So you need to look into the main function first, right? So I think that generate the GUI, right? And for this one, it's to run the code. So you can just click into the run function. Okay, so run function is quite intelligent, right? So in a run function, for example, like
first try to generate the GUI. So what I want to emphasize is the main function to do fitting. Okay, the curve fitting. So for this one is that, for example,
if you click the GUI, so it means you input given point, you interact with the GUI. For example, click one more time with your cursor, you input 1 point, right? So if you input like 10 points, so it's going to be like saved in a current point P, and okay, this means you get all the data. For example, if you get 20 points, you get 20 XY, right? So saved in the vector, and finally do the fitting of the curve, you can get to A, B, C. So you're going to get to the A and B, right? So the A, B means, okay, you can just, okay, you can plot the curve, plot the line. So it means it goes to this function, okay, fit curve. So fit curve function. Okay, so the fit curve function is directly coming from the function of Python.
Only from the another Python code. Fit curve in the left and left.
okay. So this
This is for the curve. The fit line is to fit.
oh the list square. This is from Python.
Yeah.
So we find a list
Script this is from Python. So it's going to be
directly solve this
equations. So those are all the linear functions, right? Linear plus and minus. It means finally that can be like I mean simplified into a single equations from B, and that can be simplified. Okay, you only get 2 equations, you can solve it efficiently. So this is corresponding to this function. Okay, this is finally coming from okay. From this library. Okay.
It's coming from this library. So, for example, like if you do the machine,
maybe you have to use the Sklearn. Okay, Sklearn is another library. You can do some basic functions for the machine learning. Okay, KD tree decision making. And also for if you're working with the data analysis, you can look into the Pandas. Okay, Pandas is a good toolbox for the data input and output. Okay, so if you not replicate the demo, so you can try offline. And if you still not do it, so okay, you can raise your issues.
you can raise your issues in this GitHub issues. Okay. So if you have any questions, you can just new issues. Click this one. Of course, you need to have a GitHub account first. Okay, you can log in and also open the new issues. And later our TA will look at the
issues and reply to you. Will reply to you. So any questions? So for example, in a like
after lecture you can make some modification with the code. Okay. So for example, you can learn from Python, for example, okay. So let's see the function for
this script. You can, for example, I want to know how many seconds your converter right to solve this equation, to solve this function. So you can learn from ChatGPT to ask ChatGPT, say, so like calculate the time differences. So ChatGPT provide some example code based on Python. For example, to evaluate like how many milliseconds this code will be used to solve this square estimation problem. And also you can gradually like increase the number for points to see if the computation load, the computation time will increase or not. Okay, you can do some modification based on the codes. And I want to share is,
as we mentioned, okay, the series. Okay, the series. This is the open source, solvers
for linear optimization problem. So here
there is, okay, just search from online. You can just search from online. So in here, okay, there is a tutorial. This is the wiki for the series. There is a tutorial for the nonlinear least square.
So you see, they provide a lot of examples. For example, if
you scroll down,
if you want to minimize, for example, the four-dimension problem, okay? X, 1, 2, 3, 4, 4 no variables. So if you want to simultaneously minimize the 5 cost function to find the big point X, Y, X1, Y, X1, X2, X3, X4 to minimize the summation. Okay, this is a linear optimization problem. Okay, you can get into those tutorials to have understanding. Okay, I want to say like a lot of things can be learned with those coding examples. Okay. So that's all for today's lecture. So I'm going to thank you for additional 5 minutes. Okay. If you have any questions, feel free to come. So if there's no questions, you can dismiss. Okay. Okay, no lectures next week. Okay, no lectures next week. No lectures next week. Okay. Okay, see you next week.